Chapter 8 is about the sedimentary basins and the petroleum system. So it's now that we have a bigger scale. So we are zooming out from the traps and the seals. And then one basin can have several or tens of accumulations. So the basin scale is much bigger, and we're going to just explore how these basins are formed and why they are important in the petroleum geology, okay, and the petroleum exploration. So sedimentary basin, I think we talked about this before. Basin, when we say basin, it's like a plain and maybe like flat surfaces, right? Surrounded by some mountains, right? But it doesn't have to be on the surface. It can be in subsurface. Right? A sedimentary basin is an area of Earth's crust that is underlain by a sequence of sedimentary rock. And keep in mind that the sedimentary basin doesn't have to be a place on the surface. And it doesn't have to be a closed contour like a washbowl. So then the questions related to sedimentary basin are these. Let's read this because these are very important. What is the size and shape of the basin, and how did these change as the basin was filled? So you can think the basin as a bowl shape, like just simply, but it doesn't have to be bowl, but this bowl can be formed before the petroleum is coming, right? Or the petroleum is migrated to some sedimentary rock, and then they can be deformed. Right? So this kind of chronology is also important. And when you have a bowl shape of surface, then there will be some sediments coming in. More sediments are coming in, and it will be filled eventually. Right? It's called the infill. And the second question is the basin floored by continental crust or oceanic crust? And what kinds of, and what proportion of the sediments are filling that basin? So is it a lot of fine fractions, or is it very clean, or well sorted sand, or well graded sand, or those kind of questions. Right? What are the sources of the sediment, and by what pathways was it transported to the depositional site? And I'm reading it here. What was the history of the filling of the basin? How can the original geometry of the basin be distinguished from subsequent deformation of the basin? And what was the overall tectonic setting of the basin? So we'll keep in mind these questions as we go through this chapter. So the contents are these. Today we'll talk about the basic concepts and terms of the basin and mechanism, how they are formed. And then classification of the sedimentary basin. And these are the type of the basin actually. Cratonic basins and trough, lift drifts, and strike slip basins are each type of the basin. So today I think we'll have time to cover up to 8.5, so troughs. So definition again, the sedimentary basin is an area of the Earth's surface where the sedimentary have accumulated to a greater thickness than they have in adjacent area. So if the sediments are quite thick to the adjacent area, so when you look at the thickness, then this is called a basin. And hydrocarbon commonly occur in sedimentary basin because sedimentary basins are permeable and with high porosity. It has a better and good geometry to be trapped. And strong evidence for the sedimentary organic origin of the hydrocarbon also supports the current occurrence of the hydrocarbon in sedimentary basin. Basins formed as a result of the cluster thinning and rifting. So basins are scale of 100 kilometers. So it's mainly formed by tectonic movement. So we're going to see how each tectonic movement affects the basin formation. So some coastal area you have a compression, and some area you will have a tension, right? Also you can have shearing, and these can affect the basin formation. So it doesn't have criteria in terms of the size. It can be very large and it can be very small. So in terms of length, typically it's more than 100 kilometer, and width is more than 10 kilometer. So basin, when you have a basin like a bowl shape, then the width and length will be pretty similar size, but sometimes it's very elongated shape. So then the width can be thinner than the length. The area is typically more than 10,000 square kilometer, and the thickness, basin thickness about 5 kilometers. So we're talking about the layer of like formations from like Jurassic to Miocene or Precambrian or something like that. As I talked just before, the sedimentary basin indicates that you have a like bowl shape, and then the sediment is coming, right? So chronological order is also important. Subsidence and the deposition took place simultaneously. In this case, it's called the syn depositional basin. So that's the case in here, the right side. So as it deforms, you have sediments coming in, filling it. Right? And if not, it's called a post-depositional basin. So you have deformation first, and then deposition coming after that. The syn depositional and post-depositional basin. And distinction between these two types of basin is critically important in petroleum exploration because of the need for traps to be formed before hydrocarbon generation is migration. So which one is first generated, it can tell you that whether this basin is proporous or it's rich in hydrocarbon or it's poor in hydrocarbon. Stratigraphic traps are generally formed before petroleum migration, and structural traps may predate or postdate the migration. So structural trap can be found in post-depositional basin, and stratigraphic traps are also found in the syn depositional traps, basins. And the mechanism of so when we talk about the mechanism of the basin formation, it's mostly about the tectonic movement. So we have to look at the structure of the Earth first. So we know that the Earth is about, diameter is about 6,400 kilometers, right? So here it says 6,000, diameter is about 6,370 kilometers. Right? In terms of the chemical property, you have an iron-rich core and mantle. And mantle is rich in silicate, right? Silica and oxygen, and you have a crust. In terms of the physical property, you have an inner core, which is solid, and outer core, that's liquid, and the mesosphere, right? That's similar. I think it's the same with the mantle, it's a solid, and the asthenosphere, which is a mantle that flows, and it has a convective flow, and the lithosphere is corresponding to the crust, right? That floats on the mantle and that moves together with the mantle. So you look at the depths. Lithosphere is about 0 to 100 kilometer deep, and asthenosphere is up to 500 kilometer, and the mesosphere is here. And when we say crust, depending on the oceanic or continental, it can be like 8 kilometers thick, and the continental crust has a thicker, right, thickness. So lithosphere is made up of series of rigid places, and lithospheric plates drift slowly across the asthenosphere. The asthenosphere is the one that flow convectively. And when we say the continental crust and the oceanic crust, they are very different because of the main components chemical components are different. Continent is granitic, so it's made of granite. The density is about 2.8. Here, 2.8. And the oceanic crust is made of basalt. So it's 2.9. Right? So oceanic crust is much heavier. It's not much, but there are density difference. Right? And sedimentary basins, yep. So granitic continental crust and the basaltic oceanic crust. And when you look at the density of the subcrustal lithosphere, that's about 3.3 gram per cubic centimeter. So it's much denser than the near surface crust. So I think with these pictures may be very familiar to you. Right? You've seen this picture in high school geophysics or the earth science class, right? So we have here, what do we have? We have ocean, and the crust is generated from the ridge, right? Oceanic ridge at the divergent boundary. And it moves, and then it goes to trench and subductive zone, right? The convergent boundary, here, trench. And sometimes you have a fault, right? And what do we have here? Hotspot. Right? And when you have a subduction zone, there's a arc, island, right? And you have a basin formed here. And you can have volcano area and also a lot of earthquake generated in the subduction zone and ridge and the fault, right? And or island arc here, right? Rising magma and ocean, what do we have here? Oceans are young. So oceanic crusts are young near this ridge because they are generated just now. And as they move to the plate boundary, here the convergent boundary, it becomes older. And the oceans are floored with basaltic volcano rocks. So this is just basic pictures that you need to keep in mind. Then, because of this kind of a tectonic the movement of the crust, it forms the like bowl shape, or it can form some deformed surface, subsurface topology. Then you have a sediment filling in, and it forms the basin. Another pictures, like you have convective flow in the asthenosphere, right? So here's the ridge, and the trench, and the subduction. And what do we have? Crust, ridge valley, island arc, magma, and cold. So when the geothermal gradient is also different where you're looking at, right? So in this, around the oceanic ridge, because they are new crust is developed from the deeper region, right? So the heat flow will be very high. Right? So geothermal gradient will be high in the around this ridge area, right, where the plate is generated. Right? And what about here? So as it flows and moves to this side, it became cool, right? It's cooling down so that you have low geothermal gradient in this region. So plate is relatively cool, and here the relatively is hot. Okay. And then how this oceanic basin forms, right? You have ridge, right? On the axis of the seafloor spreading, then the tension develops, and because of the tension, there was some horst and graben, right? And then it fills above it, and it becomes the oceanic basin. And deep basin undergo extensive tectonism as their sediments are compressed by the converging plates. Intracratonic basins develop intermittently on areas of the continental crust. Okay. So you can see that here the black area is indicating the sedimentary basin. When there's a crust deformation, then sediments are coming in and then it's filling the void. Just for your reference, I think you've seen these kind of pictures when we study earthquake. Right? The mid-ocean ridge is somewhere here, right? And the plates are moving. These are the ridges, the plates are created. And then it moves, and there's a subduction zone here, and also here is a fault. This is fault. Right? And mid-Atlantic ridge also generates the plate and the crust. And there's a subduction zone. And we know that around the Himalayan and Nepal area, there's a lot of earthquake, right? And there's also a subduction and crust. Continental crust is meeting another continental crust, so that there's a subduction zone too. Yep, these are the rift, oceanic ridge, and here you can see one subduction plate boundary, convergent boundary. Here is the divergent boundary. And what else? San Andreas Fault, just close to California. Also, there are a lot of earthquakes, and that is by this fault movement, transcurrent movement, and along the Peru and Chile also we know that there are a lot of earthquake activity. That's because of this subductive plate boundary. What else? And Indonesia, right? There were also tsunami and the earthquake before, and here the plates are moving this direction, right? And there's a subduction zone also here, right? And this is just near the Japan. Right? So basin can be formed in 4 different mechanisms, and here the figure is showing the 3 mechanisms. Crust compression. So the one crust is going down, and these 2 crusts are compressing each other. So this happens in the subduction zone or the trough. And crust tension is where you have a ridge, right? So it's a divergent plate, and have a fault generated, and the sediments are coming in and they fills it. And also sometimes you have a burst or depression of the subsurface, and you can have the basin can be generated. So let's look at one by one. Then here is the one mechanism by the crustal tension. And crustal tension at the zones of the seafloor spreading is a divergent plate boundary. And because of the tension, it forms a normal fault. And it's called a lift basin. So tension generates the normal fault, and after this normal faulting, then the sediments are filling it, so they form the sedimentary, the lift basin. It's called a lift drift sequence. And the second mechanism is because of the compression. Just before it was tension, right? And crustal compression at the convergent plate boundary. Then you have a thrust fault, and it's a four-land basin forms. So here, when you have a crustal compression at the convergent plate boundary, actually there are two basins can be formed. So you have a fore-arc basin, and there's a back-arc basin, and we're going to talk about it later. Here, back-arc, and here, fore-arc basin. Actually, it's in the later slide. We'll get to that soon. And as a result of the vertical crustal movement, that's the third option, third mechanism, and phase changes can take place beneath the lithosphere. These changes may take the form of the localized cooling, and therefore the contraction resulting in a superficial hollow which becomes infilled by sediment. And the lithosphere may locally heat up and expand, causing the continental crust to dome. Erosion follows and creates a hollow for sediments to fill in and cooling. And the last mechanism is, it was not in the picture, but it's a simple crustal loading due to sedimentation. Actually, it's chicken and egg problem, because when you have a, let's say that you have some kind of a crustal like this, and this can be deformed, and then the sediments can form, right? Or you have a sediment form, and then after that it deforms together, right? So that's why it's called the chicken and egg problem. Basins of this type require an initial depression in the crust before deposition may begin. Thus, loaded basins characterize continental margins, whereas prograding delta can initiate and maintain the depression of adjacent oceanic crust. And crustal thinning and lifting are of particular interest to the petroleum exploration, because they are an important habitat for petroleum. So crustal thinning and lifting. And many theories have been proposed to explain this simple crustal loading. I think here 3 theories are introduced. One is by Serbeson. I think it's just a simple tension and deformed by brittle failure. And here, below it, you have a lithosphere which is ductile, so it's been thinned. You can see it's been thinning. And this model was largely based on the studies of West Sea and the Gulf of Suez lift system. And the second is the Mackenzie model. And Mackenzie proposed a model that assumes that both crust and subcrustal lithosphere deformed by a brittle failure. And this model was largely based on studies of the North Sea basin. So you have a stretching, and this is crust. Lithosphere. And so in geology, actually, particularly in the tectonism or the geodynamism, here people think that this crust and the lithosphere as a layer system. And And because these two are chemically and physically different, so they can be detached or they can deform together. Right? Crust has like 2.8 gram per cubic centimeter density, or 2.9, and lithosphere is much denser, right? 3.3. So these theories are to explain these two layers and how they get deformed or developing a fault. So you can read it through. And the third is the Wernicke model, a model for cluster thinning by simple shear. So it just assumes the simple shear develops this deformation, and then there's an infill sediments coming in. So we talked about the cluster compression, tension, or just vertical movement, and then erosion coming in so that you can have deformed shape, or the loading, the simple load condition at the crust is the last theory. So then as a result of this tectonic movement, there are basins formed. Right? And depending on the mechanism, we can categorize the basins. And Cratonic Basin here, and trough at the convergent plate boundary, and transcurrent plate boundary is at the fault, and lift drift is at the divergent plate boundary. So we're gonna go over one by one. We've already noticed transcurrent plate boundary is where the plate boundaries are moving in different directions. So you have a large fault, and they can make a basin-like structure. So first, let's look at the basins unrelated to plate boundary, intracratonic basin, and these are the basins related to convergent plate boundary and related to divergent plate boundary and transform boundary here. So we'll see one by one. The first is the cratonic boundaries. Cratonic boundary is not related to the plate boundary. Subcircular basin that lies wholly or dominantly on the granitic continental crust is called the cratonic boundary. If there are basins inside the continental crust and making a semicircle shape, it's called the intracratonic. If they are overlap on the oceanic crust like this, then it's called the epicratonic embayment. Embayment is what? It's a 만, 우리나라 말로 하면. So this is the epicratonic and this is intracratonic. So let's look at the example of the intracratonic basin. This is the terragenous, so it's on the continent, dominated by continental clastics with negligible or no marine shale. Because it's in near the inland, or it exists on the continental crust, so actually the intracratonic basins have very few marine shale or the marine sediments. And around the Libya, this is Libya, where's Libya? Is it different? And Mujuk and Kufra Basin provide a good example of the intracratonic basin. So here, Kufra Basin and Mujuk Basin. And these are the location of the basin. And these basins are separated from one another by ridges of the Precambrian igneous and metamorphic basement, floored with widespread pan-Saharan Paleozoic sequence, and became structurally enclosed basin after the deposition of the continental Mesozoic. and deposition is barren of the fossils and is considered to range in age from Triassic to lower Cretaceous. So these are the main characteristics. Is there a, it doesn't have the section view, but the thin, relatively the thin sedimentary fill, 2 kilometer thick and the 3 kilometer thick. So before, when we talked about the basin, typically it's more than 5 kilometers thick, right? So comparing to those kind of typical basin, it's the thickness of the sediment is quite thin, and non-marine sand, a shortage of the organic-rich source bed, which reflects the shortage of the marine shale. Basin floor show uniform deep. Poor prospects. So because of the shortage of the marine shale, right? Marine shale, existence of the marine shale is very key for the source rock. Right? So you have a marine shale deposited with the organic rich environment, and then you have a source rock, and because there's no abundance, it's now abundant in the marine shale, so it's a poor prospect for the hydrocarbon exploration. And also it's a shortage of the mature source rock and the structure. But occasionally, or locally, you can find some hydrocarbon. Okay. That's a heterogeneous intracratonic basin. And the second type of the cratonic basin is epicratonic embayment. So that lies on the edge of the continental crust. So it's near the oceanic crust. So it's a higher potential for the hydrocarbon. And these are the example, heterogeneous embayment and the carbonate field embayment. So the one example is the tertiary Gulf Coast of the US. Here, if you're looking at, this is the Miami, right, Florida, right? And Georgia, where is Texas, somewhere is Texas here, right? So when you look at the cross section from here to here, so you can imagine that as you go toward this direction, it's crust, continental crust, and this direction is oceanic crust. Right? And section view here, so crustal continent, continental crust, and oceanic crust, and you have a basin-like structure. And P is, I think from here to from up to down, it's more recent to the older sediment, right? Eocene, Oligocene, Miocene, and Pliocene. And so scale, when you look at the scale, it's what, 15 kilometer thick sediment, and it overlies, Louisiana salt is overlying this basement, and you can see that the salt is booming up. So you have a salt dome structure. So around this salt dome structure, you can have each individual traps and the accumulation of the hydrocarbon. Right? So this is just to give you a picture how the basin is very big, and the traps are locally placed around, or they are created around this salt zone. Right? And the other also example is the Niger embayment of the West Africa, and it plunges from continental to oceanic crust. And you can see here is the oceanic crust, Atlantic Ocean. It's a granitic crust, which is going to continental crust. So it's a several 100 kilometer long basin, and you can see a lot of fault. Major fault has been developed, and so along the fault, right, you may have fault-related traps and seals. The oil and gas are regularly distributed within each major growth fault. Okay, the other one is the carbonate epicratonic basin. carbonate is very promising, and it's a kind of evidence to show you that you may have good hydrocarbon potential because carbonate can form in the marine. So here I think we've seen the Intracratonic Basin, Muzuk, and the Capra in the Libya. Here, this is the sea, and you have a, I don't know how to pronounce it, but the Sirte embayment of the Libya. And these are the lithology from Precambrian to the recent formation. And these are the formation that has bearing the oil and gas. And lower Eocene consists up to a kilometer of interbedded evaporite and carbonate. Lower Eocene is this is the lower Eocene formation, and this is carbonate. I think this is carbonate. Limestone. So typically limestone is expressed as a brick, and this one is salt, evaporite. So, and the carbonate sediments continue in the middle Eocene here, right? These are the carbonate, and to be succeeded by the shallow marine and fluvial sand and the shales from the Oligocene to recent. Here you have these are this sedimentary rock sandstone formation, and this one, right, is shale, right? Fine soil. And this is basement, right? Could be basaltic or granitic. So the main play in this basin is combination trap sealed by the unconformity. So pre-Cambrian granites through the various sandstone from Cambrian to lower Cretaceous. So here, where is it? From here to here, right? Pre-Cambrian basin, basement to Cretaceous formation is the major play. And second major play is the Upper Cretaceous Paleocene ripple carbonate. And the third major play is the recent formation here, the Oligocene sand. So it shows that vertically in the trapped and basin, you may have several layers that is producible or that give you the economical hydrocarbon production potential. So this is the feature of the epicratonic embayments. Epicratonic embayments are far more prospective than the intracratonic basin. And this is true of both terrigenous and carbonate embayment. And not only do they contain more marine sediments, therefore better source potential, but they occur where the continental crust is thinner and less stable. So it has a higher chance, likelihood to form the ceiling or trap structure. Heat flow is high, which favors hydrocarbon generation in areas of high geothermal gradient due to overpressure. Crustal instability also favors structural entrapment of the oil, as well as stratigraphic and unconformity and gross fault-related traps. Okay, and the second type is the basin related to convergent plate boundary. So convergent plate boundary is what? It's a trough or the subduction zone, right? And back arc basin and fore arc basin and the trenches. Okay. Troughs are linear basins which are far larger and more complex in structures than the cratonic basins. There are three types of subduction zone between areas of continental crust. So you have continental crust meeting another continental crust, or you have oceanic crust meeting continental crust, or oceanic crust meeting another oceanic crust. So depending on the which crust is meeting other, you have 3 different types. And Alps, Zagros, Himalaya is the continental crust. Alps is, I don't know, do we have the pictures? Ooh. Alps is here. Zagros is in the Middle East here. And the Himalaya here is a continental crust is meeting another continental crust. And oceanic and continental Cordillera North America around here. And Andes is here, right? South America. And Bangda Arc is near the Indonesia here. And oceanic crust, Japanese and the New Zealand arc here. Oceanic crust meeting another oceanic, also here. So major subduction zones are listed. So back arc trough first. Asymmetry shelves, I think, okay. This gives you the basic idea. You have a crust coming in, right? And so these are going down, and this is the continental crust. And then you have a island arc. This is the arc, like Japan. Right? And where the volcanic activities are very high. Then here's the fore arc, and this is the back arc. So if we think about the around the Korea and the Japan system, this is the Ulum Basin. In the East Sea. And here is the Japan, and the east side of the Japan is the fore arc basin. Okay. This basin contains a wedge of sediments that thickens westward some 5 kilometers until it is abruptly truncated by the Rocky Mountain thrust belt. So this shows actually the example. Western Canada, you have a back arc basin. Here, plate is going down, and this is the Rocky Mountain. So when you look at the section, this is the Rocky Mountain, and this is going down, right? And truncated by the mountain. So it's just cut by the mountain. And here, this basin-like space has been filled by the sediments. Right? And in this sediment and basin, there are several oil and gas plays. Here, the black dots are the oil and gas field. So it's in the Canada, actually, Western Canada. Right? As you go here, it's a Vancouver. So earlier Paleozoic sediment include sand, carbonate, organic-rich shale, evaporite. Major oil and gas production occurs in Devonian reefs. And recoverable reserves are estimated at 16.3 billion barrels of oil and 94 trillion cubic feet of gas. So in Canada, when you go, I think around here it's a Calgary, and Ottawa is very rich in the oil and gas industry. You can these sands are thus mineralogically and texturally mature and have a good porous dam permeability. As the arc rises, it begins to shed detritus into the back arc basin. And other example is around Indonesia. Continental crust of the Sunday Shelf moved westward toward the Indian Ocean plate. Continental plate is toward the westward, right? Here, and the subducting oceanic plate is going down. And Australian plate is causing subduction. these basins are infilled with a series of Eocene with synchro-grading clastic wedges in Sumatra Borneo Basin, with the carbonate over more stable southeastern part of the shelf. These basins are more than 10 fields with recoverable reserves in excess of 8 billion barrels of oil and 24 trillion cubic of the field. So I think this is Malaysia, Indonesia. What do we have? Here the back arc is basin, the fore arc basin, and a lot of volcanic activity. So this is going in this direction, and this is subducting plate, and continental crust is also moving toward the southwest. So main petroleum producing basins are this dotted region here. Just for your reference. Okay. So back arc basins are separated from the fore arc basin by a volcanic arc. So you have an arc here, and fore arc basins are infilled with marine sediment. Here it's near the marine sediment. And fore arc are gradually being subjected between the Indian and Sunda plates. Thrust slices thus appear locally as an outer non-volcanic island. So fore arc is relatively barren. So the hydro production from the fore arc basin is negligible for several reasons. But the back arc basin has good potential for source rock sedimentation and also the hydrocarbon potential. Traps in back arc basins are numerous and varied because you have a clay blanket. So with this combination of the favorable reservoir rocks and source rock and trap diversity, the back arc basins are commonly major hydrocarbon provinces. So then fore arc trough, you have arc here, and you can have several types of basin. First, this one is the intramassive basin, and this one is residual basin, and this is accretionary. And fourth is the constructive basin, and the composite basin is in the next slide. And this one, and 5 here, right? And these basins make less productive hydrocarbon provinces than do back arc basin. Sands are generally of the poorer quality, lacking the polycyclic and the reworked history of the back arc basin. And carbonate reservoirs are generally absent, and source rock may be abundant and of good quality because of the prevalence of the deep sea floor condition. But geothermal gradient often too low because the cool plates are being subducted, which depresses the isotherm. And the hydrocarbons are more commonly trapped in structural fault and fault trapped than in stratigraphic ones. Extensive structural deformation may cause traps to be small and hard to develop. But in some cases, fore arc basins are productive, and those tends to have fairways on their continental side and to have a broad shelf. And these are the example of those. And we have the pictures. In the Alaska, there are a lot of natural gas reservoir. and these are the, that's it, right? Yeah. These are the 4-arc basin, and this is the, some cases that you have a hydrocarbon reservoir in the 4-arc basin. Okay. So I gave you the assignment, the last assignment, and the problem 3 is about exploring the geology structure and the hydrocarbon potential of 2 basins. One basin is the Seohan Basin in west side of the North Korea, just near the China in the Yellow Sea, and the Ulleung Basin in the East Sea. So also there are some references and the papers attached together, and you can research the area in the context of the basin, trap, and sediment and the hydrocarbon potential. So review the articles, and maybe you can apply the knowledge that we covered in this chapter for your homework.